All right, today is July 17th. This will be the last day where you meet as a team and work through this. I will be back on Thursday the 19th, and very excited about that. So today we're just going to finish up our lateral thinking discussion with the third tool in our lateral thinking grab bag that we're going to use, and it's relatively simple, so it won't take long to go through it. There's a few examples I want to share, but it's also incredibly valuable for solving certain kinds of problems. And so we're going to again apply it to the concept of the problem of rush hour. And in that case, you've probably indirectly come to some of the conclusions by now using the other techniques. But um, in looking at the problem of rush hour, it's certainly a good candidate for the use of this last technique, which is called working backwards. So download the worksheet for what you're going to turn in, team names, student names, your selfie, and then you're going to apply the method we're about to learn to the problem of rush hour. So specifically, how would you trace the problem from its effects back to its root causes? And then based on the root causes, what solutions can you find? Because often, if we can figure out the root cause of a problem, we can often come up with relatively straightforward and effective solutions that we know will fix the often complex effects of the problem. So getting to the root cause is definitely advantageous for us. So let's look at this. So working backwards. So as far as a technique, it really is it's very intuitive. You just start at the end of the problem or the effect of the problem, and you start tracing your way backward to where did this problem start? Why did it start that way? Or you go to the very end of like a math problem or a complex, how do I do this? You visualize the end of that process, and therein lies the answer. And from there, it's often easier than to back into the start. So if you're looking at a problem like rush hour, you're looking at the effects of it. So we need to get to the root cause. And there's a different type of problem where what you really need to do is you need to connect the beginning to the end. So you need to solve the problem. But in solving the problem, you need to figure out how to connect the beginning to the end. So a few examples of that. So 32 football teams participate in a competition. The 32 teams are paired off, the loser is eliminated, and the remaining teams play until there's a champion. How many games must be played? Now you could do brackets and have a single elimination bracket, which is what this is, and you could count up all the games that are played and do all the math, and you could come up with the answer. But if you looked at this and it said, there's 200,000 teams that are participating in a competition, that would be harder to draw all those brackets. So we don't want to just do the manual. Let's write it out and see. For this one, we want to try and be clever and see if we can work backwards. So if you're looking at this, it's hard to maybe visually see, how many brackets there are and how that would look. But if you look at the very end of this problem, there's one champion. And so the thing that makes this problem really quite simple is the fact that it's single elimination. So the loser is eliminated from each game, and the teams are 1 against 1, so that makes it nice. And the remaining teams play until there's a champion. So from that standpoint, if you think about these 32 teams, where do they end up at the end of this process? Well, there's just one champion, so there must be 32 minus 1 losers, so teams that have lost. So we have that. So we have 31 losers and 1 winner. You might say, okay, that's, kind of knew that, no big deal. But here's the thing. If there's 31 losers, how often does someone lose a game? And the answer is you only lose once in a game, and each game only has one loser. So the question that we're being asked is how many games must be played? And if each game creates one and only one loser, there's 31 losers, then there must be 31 games. Now, if you do the brackets and do the math, you'll find that you're right, but it's hard to intuitively say, oh, 32 football teams, let's do the brackets, and you're not sure where you're going to come up with. But if someone just said, yeah, 31 games, it wouldn't seem like the logical answer. But if you follow it by working backwards and saying, what does the end game look like? Well, one champion, 31 losers. Each game creates one loser, so there must be 31 games. So another one is a little more complex. In order to decide which of his two sons would inherit his fortune, an old king tells them to race their horses to a distant city. The son whose horse arrives last will win. After days of wandering, the brothers ask a wise man for advice. They then run to their horses and race off toward the city as fast as possible. What was the wise man's advice? So this is almost a combination of working backwards and destroying assumptions. Because if you read through it, you make additional rules to the king's game that aren't there. So an old king tells them to race their horses to a distant city. We assume by their horses he means their own horse. But here he specifies, the son whose horse arrives last will win. And so really the indication of winning or losing has nothing to do with the sons. It has to do with the horses of which each son owns that horse. So because of that, the sons are actually not part of this race at all, except he tells them to race their horses to a distant city. So they should be some part of that, but the key indication of winning is you have to arrive last. And so you can't race backwards to where the one who arrives last will win, because the best thing that you can do is just stop and go zero in terms of speed. So that's not going to work. But then the wise man, tells them, oh, you're assuming that you have to race your own horse, because you can't race at zero, you'll never get anywhere. So you want to have that urgency, that effort. But if you switch horses, then you're driving like a normal race, because you want your horse to arrive last, meaning you want your opponent's horse to arrive first. And therefore, we can have a regular race by you jumping on each other's horses and then going. So it's another working backwards problem. Okay, so this, I'm going to let you choose how much you dig into this, but this is a fun example of, and there's a YouTube video of the actual video of when this happened. So NASA astronauts, by this point, this was Apollo, I think 17, and they had kind of figured out how to be on the moon at that point, and they had a lunar rover that they drove around and did experiments with. One problem they had, though, you see how new and clean the spacesuit is before they get up to space, and then once it's there, well, I think we talked about this when we were working through the critical thinking exercise, but moon dust is basically like diamond sandpaper, just rips apart everything it touches. It also holds in heat very well, so if the sun is shining on the moon, that's very, very hot. So if it's all over you, it's going to melt through your suit potentially. So because of that, this was a real problem. So they had a lunar rover, and one of the guys was fixing the rover with a hammer and accidentally hit the dust flap, and it ripped off. They weren't able to put it back on. They just arrived, and they had like 2 weeks of explorations planned, and without that dust flap, the dust would fly in the air, it covered all their equipment and them, and it wasn't a good situation at all. So they realized very quickly, without that, they weren't going to be able to use the rover at all, and that was the whole reason they came there. So what they ended up doing was they ended up assessing everything that they had in their lander and the rover, everything else, and they visualized what would solve the problem. So they didn't look at that and say, how can we solve the problem? They first started and said, what would solve the problem? Well, we need something that is reasonably um, solid, but it doesn't have to be all that solid. Because the other one was made out of metal. It doesn't have to be all that solid. It just has to bounce little bits of dust back down. So it can't be porous, but we'd like it to be somewhat bendable so we can bend it to the shape we need. And then from there, we just need it light enough that we can clamp it without it falling apart. And so what they ended up using was their laminated lunar maps and duct tape to make the mud flap itself. And then they took off some lab equipment that they had on the lander and got some clamps from that and clamped it on. Whereas the mud flap itself was too expensive or too heavy to do that, they used their clamps. This was very lightweight, and they solved the problem. And they were able to, make use of those multi-billion dollars of effort that it took to get there and do all their experiments. And in fact, this mud flap that they crafted on the moon, they brought back with them and is in the Smithsonian, so you can see this actual mud flap. So it's another example of working backwards. So what I want you to do is I want you to apply that to rush hour. So think about the end state. Think about the effects of everyone there and not being able to move quickly enough. And I want you to work backwards. So this, in part, it will likely cross over to the destroying assumptions, but I want you to start at the end of all those effects and think through on how could we get to the end result of what they're trying to do, why people are involved with rush hour, what is their purpose, and how can we back that out to where they could avoid the whole rush hour part and still accomplish their goal. So that's it. So submit that once you get that done, and I will see you guys on Thursday.